All right, recording looks good. Let's go get started with this Math 221 exam. So, to start, question 1, we have evaluate the limit if it exists. If the limit does not exist, state whether it's infinity, minus infinity, or neither, and fully explain its behavior. If you use a theorem, like the squeeze theorem or L'Hopital's, clearly state which theorem you're using and why it applies. So, let's get started with this first question, part A. We have the limit as x approaches 0 of 1 minus e to the 2x plus 2x, all of that over x sine x. So for these limits, first thing you always want to try is just plugging in whatever value you're given. So in this case, we have 0, so we have 1 minus e to the 0 plus 0 all over 0 sine of 0. This will simplify to 1 minus e to the 0 is just 1. We can ignore this other 0. And on the bottom, 0 sine 0 is just 0. This just gives us 0 over 0, which is going to be one of our indeterminate forms. And because it's this fractional one, this actually implies that we can use L'Hopital's. L'Hopital's, I'll just write it explicitly. Just in case you forgot, L'Hopital's is a rule we can use whenever we have a limit in the form of f of x over g of x that gives us one of those indeterminate forms, right? Like 0 over 0 or infinity over infinity, one of these fractional ones. And with L'Hopital's, we can rewrite it as the limit of f prime of x over g prime of x. And yeah, hopefully that makes it a bit simpler. And for right now, what I'll do is I'll indicate this with a little equivalence and an L with a circle. So with this, we can rewrite our original limit as equivalent to the limit as x approaches 0 of the derivative of 1 is just 0, so we can ignore it. And then we subtract the derivative of e to the 2x is just 2e to the 2x. And the derivative of plus 2x is just plus 2. Now for this bottom bit, the derivative of x sine x, we can use the product rule. So the derivative of the first times the second plus the derivative of the second, which will be cosine, times the first. And I'm just writing it in reverse order, so it's a bit easier. Now again, we'll just plug in 0, and we'll get minus 2 times e to the 0 plus 2 all over sine of 0 plus 0 cosine 0. This just gives us minus 2 plus 2 all over 0 plus 0, which again is 0 over 0, or another one of our indeterminate forms. Actually the same one, and so we can apply L'Hopital's. So now we have the limit as x approaches 0 of the derivative of this top bit is going to be minus 2 times that exact same derivative of 2e to the 2x over derivative of sine x is cosine x, and the derivative of x cosine x is going to be 1 times sine of x. No, I'm sorry, 1 times cosine of x plus we'll have x times minus sine of x. Just like that. Now plugging in 0, we'll get minus 2 times 2e to the 0 over cosine of 0 plus cosine of 0 plus 0 times a minus sine of 0. This will just give us minus 4 all over 1 plus 0, which is minus 4 over 2, which is just minus 2. And that's our first answer. Moving on to part B, we have the limit as x sine of 3 over, the limit as x approaches infinity of x sine of 3 over x. So to get started, let's just write this out. We have the limit as x approaches infinity of x sine of 3 over x. First step again, let's just plug in infinity, see what we get. We're going to get infinity times sine of 3 over infinity. This term just goes to 0. Sine of 0 is 0, so we're just going to get infinity times 0, just like this. Now this is one of our indeterminate forms, but because it's not in a fraction, like our previous problem, like you can see up here in the orange, we can't apply L'Hopital's. So what we're going to want to do is somehow turn this x sine of 3 over x equation or expression into a fraction. And we're going to do this like this. So we're going to take x sine of 3 over x. We're going to write it as a fraction over 1. Now this won't do much, but what we can do is we can multiply both the top and the bottom by 1 over x. Okay, and of course this won't change anything, but when we simplify, these x's are going to cancel on the top. We'll get sine of 3 over x all over 1 over x. And you'll see in a second, this will actually help a lot. And we know to do this just because we want a fraction for L'Hopital's, and this gives us that fraction. So this is equivalent to the limit as x approaches infinity of sine of 3 over x all over 1 over x. Now this is going to be equal to sine of 3 over infinity over 1 over infinity. And this is going to go 0, this is going to go 0, sine of 0 is 0, so this is all 0 over 0, which is an indeterminate form, and it's one of our fractional indeterminate forms. So what is that, indeterminate forms? Not sure what that is either. Indeterminate form, so we can apply L'Hopital's. All right, so by L'Hopital's, we can now take the derivative of each of these. So we'll do a bit of chain rule, so I'll write it up here just so it's clear. First, let's take the derivative of x to the power minus 1, or 1 over x. And this is just going to be a pretty easy power rule. This is going to be minus x to the minus 2. And what this also tells us is that the derivative of 3 times x to the minus 1 is just going to be minus 3x to the minus 2. And then, of course, this derivative is also applying to this one. All right, so now we can also look at the derivative of sine of 3x to the minus 2. This is just going to be equal to cosine 3x to the minus 2 times the derivative of 3x, I'm sorry, this should be minus 1. 3x to the minus 1. This is going to be our minus 3x to the minus 2. Put some parentheses around here. All right, so now we can apply L'Hopital's. This top bit, as we just saw, let's write the limit first. But as we just saw, this top bit is going to be minus 3x to the minus 2 cosine of 3x to the minus 1. This bottom bit is going to be a minus x to the minus 2. This minus x to the minus 2 is going to cancel from both the top and the bottom, and we're just going to be left with the limit as x approaches infinity of 3 cosine of 3x to the minus 1, which actually, for right now, I'll just rewrite as 3 over x. So it's a bit easier to see that when we plug infinity into this, we get 3 cosine of 3 over infinity. This goes to 0. Cosine of 0 is just going to be 1, so this is going to be equal to 3. Perfect. Pause this, grab a drink of water real quick. All right, perfect. Let's go get started on this third limit. So this one's going to be a little bit different. We have the limit as x approaches 3, but from the negative side, of the natural log of 5 over 3 minus x. So because this limit is a one-sided limit, the way we're going to do it is by just writing a table. So we're going to be starting with looking at our x values. So because we're approaching 3 from the negative side, that's going to be as we go like 2, 2.5, 2.9, 2.99. And so let's just write out some of those values. So let's say we have 2.9, 2.99, and one more, 2.999. There we go. So we're getting closer and closer to 3 from the negative side. Now let's look at what happens to 3 minus x. Well, this is just going to be 0.1, and then 0.01, and then 3 minus 2.999 is 0.001. And let's just keep going. Let's see what 5 over 3 minus x is, right? We're just going to keep expanding what term we look at in this, this expression over here. So 5 over 0.1 is just going to be 50. Then 5 over 0.01 is 500. And 5 over 0.001 is 5,000. And now last bit we have to look at is the natural log of this. So the natural log of 5 over 3 minus x. And I don't know how to calculate these natural logs without a calculator, but we can just look at them. So we're here, we have natural log of 50, natural log of 500, natural log of 5,000. And what hopefully you can see is happening is this is going to eventually approach the natural log of infinity, or at least as x gets infinitely close to 3 from the negative side. And if you remember natural log, which hopefully you do, it increases slowly, but it's always increasing. So this is just going to go to infinity, just like that. All right, perfect. Let's go ahead and move on to number 2. Get quick support. All right, question 2. Compute the following derivatives, use any method. You do not need to simplify your answer. So we have that f of t is equal to natural log of 4t squared over t squared plus 6t. So this is just going to be a pretty standard quotient rule application, so I'll just write that over here in case you forgot. The quotient rule says that if we have something like g of t over h of t, the derivative of this, d dt, sorry, the derivative of this is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all of that above the bottom part squared, just like this. So now that we have this, we're going to want to look at the derivatives of both of these portions right here, the numerator and the denominator. So let's first look at this, the numerator, because it's going to be a bit trickier. We want to take the derivative with respect to t of natural log of 4t squared. So just recall that the derivative, we'll do say with respect to u, of natural log of u is going to be u prime over u. So in this case, we can let u be equal to 4t squared. U prime is going to just be 8t. And this tells us that the derivative with respect to t of natural log 4t squared is going to be equal to 8t over 4t squared, which is just equal to 2 over t. Nice and easy. All right, and then next up, this is just going to be a pretty standard power rule application, but the derivative with respect to t of t squared plus 6t, that's just going to be equal to 2t plus 6. And I'm going to move this all over just a tiny bit because we're going to want the space. But now we can apply the quotient rule. So we have f prime of t. This is going to be equal to, we're going to do the bottom, so that's t squared plus 6t times the derivative of the top, which is 2 over t from right here. This is minus the top times the derivative of the bottom, so 2t plus 6, all over the bottom portion squared. So t squared plus 6t squared, just like that. All right, for this next one, part B, we have g of x is equal to e to the 8x, arctan of x cubed. So this is going to be, actually, I should be writing this out. G of x equals e to the 8x times arctan of x cubed. This is going to be a little bit of chain rule, a little bit of product rule. So let's first write out these two derivatives. So the derivative with respect to x of e to the 8x, I'm not going to bother writing the full u sub, but you absolutely could on your scratch paper. This is just going to be 8e to the 8x, like this. And now when we look at the derivative with respect to x of arctan x cubed, we're going to want to let u be equal to x cubed, which gives us u prime is equal to 3x squared. Recall that the derivative with respect to u of arctan u is just going to be equal to u prime over 1 plus u squared. So now we can solve the derivative with the x. So the derivative with respect to x of arctan x cubed is going to be equal to 3x squared all over 1 plus x cubed squared is going to be x to the 6th, just like this. So now let's go back to g. So g prime of x, we're going to be using product rule here, is we'll take the derivative of the first, which is going to be our 8e to the 8x, times the second, arctan of x cubed, plus the derivative of the second, which is going to be a 3x squared, over 1 plus x to the 6th, times the first, e to the 8x, just like that. And that is going to be our final answer. Now moving on to part C, we have h of t is equal to tan of sine t plus cosine t plus 5t. Again, this is just going to be chain rule here. So let's go ahead and look at the derivative with respect to t of sine t plus cosine t plus 5t. This is equal to, let me give myself some more space. The derivative of sine is cosine. The derivative of cosine is minus sine. And the derivative of 5t is just 5, like that. And now just remember that the derivative, let's say with respect to u of tan u, is going to be equal to u prime times secant squared u. Secant squared u, just like that. So if we want to look at h prime of t, we're just going to look at u prime, which is going to be this term up here, the cosine t, minus sine t, plus 5, times secant squared of u, which is just that same thing, the sine t, plus cosine t, plus 5t, just like that. And that's it. All right, last one. We're going to need the fundamental theorem of calculus for this one. So we have f of x is equal to the integral from 2 to x squared of the square root of cosine squared t plus 8 dt. All right, so the way we're going to do this is we'll take the derivative on both sides. So d dx of big F of x is equal to the derivative with respect to x of the integral 2 to x squared of the square root of cosine squared t plus 8 dt, just like that. All right, and so now, if you remember the fundamental theorem of calculus, we can simplify pretty easily. So f prime of x, this is going to be equal to square root of cosine squared, and then we're just going to plug in this top value here, cosine squared of x squared plus 8, and then we just have to multiply by our chain rule. So the derivative with respect to x of x squared is just going to be 2x, like this, and that's our answer. All right, moving on. Okay, so for question 3, we're going to compute the following integrals. Use any method from this course. You do not need to simplify our answer. So let's go ahead and let I be equal to this integral, just in case we need to refer to it. We have the integral from 1 to e of t square root t plus 1 over square root t, all of that squared dt. So the way I'm going to approach this is first by rearranging a little bit. So the integral from 1 to e of t square root t, and I may rewrite this 1 over square root t instead as square root t over t, just like this, square that, dt. And now I can factor out a square root t. So I have the square root of t, let me put my brackets around this, times t plus 1 over t, and all of this is going to be squared just like that, dt. This is now equal to the integral from 1 to e. This square root t squared term is going to turn into t, and then it's going to be multiplied by t plus 1 over t squared dt. Let's simplify, or expand, I suppose, the this is equal to the integral from 1 to e of t times, we're going to get t squared. T times 1 over t is 1. And since we have two of those, that's going to be a 2 plus 1 over t squared. Feel free, of course, to do this fully on your scratch paper. And then this is, of course, times dt. This should be t squared, sorry. Now we can integrate from 1 to e. And if we distribute this t, we get t cubed plus 2t plus 1 over t. And now we're ready to start integrating this. This is going to be equal to, we know that the integral of t cubed is going to be 1/4 t to the 4th by the power rule. 2t is going to be t squared, and 1 over t is going to be natural log of t, just like this. And we're integrating this from 1 to e. This is going to be equal to, we have 1/4 e to the 4th plus e squared plus natural log of e. And now what we can do is we can subtract. This is going to be 1/4 plus 1 plus natural log of 1. And now, if this was on my test, this is where I would box it. Because we don't need to simplify, you should just stop as soon as you have all the values, just in case you make an arithmetic mistake. I'll simplify this just a tiny bit, because there's a lot of ways you could solve this problem. We'll get 1/4 e to the 4th plus e squared. Natural log of e is just going to be 1. Then we can subtract 1/4, subtract 1, and subtract natural log of 1 is going to be 0. Okay? These two 1s are going to cancel. And I'm not going to bother factoring this e squared, but you definitely could. We're going to have 1/4 e to the 4th plus e squared and minus 1/4, just like this. And this is also our answer. So any stage of this would be totally valid. All right, next up, we have the integral from 0 to pi of x cubed sine x to the 4th dx. So the way we're going to want to do this is with u sub, because we see we have this kind of ugly term within our sign. So let's go u is equal to x to the 4th, and then we have du is equal to 4x cubed dx. And to get this 4x cubed, we're going to have to multiply by 4. And the only way we're going to be able to do this is if we I'm not sure what I just said there, if we also multiply by a 1/4 out front. So we have 1/4 times the integral from 0 to pi of 4x cubed sine x to the 4th dx. Right, because these two 4s would cancel out if we wanted them to, but we got that 4, so we can do our u sub. Now from here, we have that I is equal to the integral, or I'm sorry, 1/4 of the integral of sine u du. And now here we have to make a choice. We can either swap the bounds to our u bounds, or we can leave them as they are and swap back to x at the very end. Just because I feel like this is the best practice, so you don't forget, we're going to swap the bounds. So I'll do that up here in orange. We know when x is equal to pi, this implies u is equal to pi to the 4th. And I'm just getting that from this equation right here. And when x is equal to 0, this implies u is also equal to 0. So our new bounds, we are integrating from 0 to pi to the 4th, just like that. Now we can say this is equal to 1/4. We're ready to integrate. The integral of sine is minus cosine. That's u from 0 to pi to the 4th, just like that. And from here, we can say this is equal to, this is equal to 1/4 times a minus cosine of pi to the 4th, minus a minus cosine 0, just like that. And I think that looks about right. So again, this is where I would stop if I was taking my exam. Why bother risking that those arithmetic mistakes? But I'll simplify just in case you did it a little bit differently. We're going to have 1/4 of minus cosine pi to the 4th. Cosine of 0 is 1, And since we're subtracting a negative, this is going to be plus 1. And this gives us 1/4 times 1 minus cosine pi to the 4th. And this is probably the most simplified you'll get. All right, moving on, part C. Okay, so for part C, this one is going to be a little bit weird because of this absolute value we have right here. And whenever we deal with absolute values, the best way to do this is going to be to split it up into a piecewise function. And that's just where you have like a function defined in multiple cases almost. So the way I'm going to write this is it's going to be the same as, well, let's look at this absolute value. This absolute value is actually going to be the exact same as x plus 2 if x is greater than or equal to minus 2, right? You say we have a number like x is equal to 0. Well, 0 plus 2, the absolute value doesn't change it. So it's going to be the exact same. But let's say we have a number like minus 4. When we take our minus 4 plus 2, minus 2, and we take the absolute value, it turns it positive. So in that case, it's actually negating it. So it's minus x plus 2. And that's going to happen anytime x is less than minus 2. So now we can write our integral. We have I is equal to the integral from minus 4 to 0 of the absolute value of x plus 2 minus x dx. Now, with this function up here, we can rewrite this. We can say that I is equal to the integral. Let's go from minus 4 to minus 2, right? And I'm picking minus 2 because of this. And when we're in this negative part, we're using the negative portion. So minus x plus 2 minus x dx. Then we're going to add to that the portion from minus 2 to 0, which is x plus 2 minus x dx, just like that. Now, simplifying, we have the integral, or I is equal to the integral from minus 4 to minus 2. This is going to be minus x, minus another x is minus 2x, minus 2 dx, plus the integral from minus 2 to 0. These two x's are going to cancel, so we just have 2 dx like this. All right, now let's integrate. We have the integral of minus 2x is going to be minus x squared. Let's put some brackets around this. The integral of minus 2 is minus 2x, and this is from minus 4 to minus 2. And we're adding to this. Let's put this in brackets. The integral of 2, which is just 2x, this goes from minus 2 to 0, just like that. All right, now we can say I is equal to, this is going to be a long expression. So minus, let's put some parentheses in here as well, x squared, and we're looking at this minus 4 first. We can just write this as, no, I'm sorry, we're looking at the minus 2 first. I knew that felt weird. This can just be written as 4, right? Because minus 2 squared is 4. And then we are going to subtract 2 times minus 2, just like this. And put those parentheses, there we go. Now we're subtracting from that the minus 4 portion. So this is going to be minus 4 squared is 16 minus a 2 times minus 4, just like that, parentheses. And now we're going to add to this 2 times 0, that's better, much nicer, and subtract from that a 2 times a minus 2, just like that. All right, again, if this was my exam, I would absolutely just stop here, box my answer, that's all I need. Because you could probably do this in a couple ways, I'll go ahead and simplify just a bit. This is going to be minus 4 up here. Minus 2 times minus 2 is plus 4. So this is going to cancel a 0. And then we are subtracting minus 16 plus 8. Okay, and then over here we are adding a, let's put this in parentheses. 2 times minus 2 is a minus 4, and then of course we have the other negative out front. This is going to go to 0, this is going to become positive 8, and this is going to become positive 4 for our final answer of 12, which is, again, a nicer answer. All right, last integral, I believe. Yep. Okay, so for this one, we have an indefinite integral. So we have the integral of e to the 2x over the square root of e to the x plus 1. So because we have kind of some weird values in our radicals, we're going to want to use u sub. So we have u is equal to e to the x plus 1. Du is going to be equal to e to the x dx. And last thing we're going to need is e to the x is equal to u minus 1. So let's go ahead and rewrite our integral as the integral of e to the x over square root e to the x plus 1 times e to the x dx. And now you can see we can substitute quite easily. We have the integral of e to the x turns into u minus 1 all over the square root of u times du. Nice and easy. This is going to be equal to the integral. We're going to split this to u over, and then let's rewrite square root of u as u to the 1/2 minus 1 over u to the 1/2 all times du, just like that. Let's keep simplifying. We have the integral of u over u to the 1/2 is u to the 1/2 minus 1 over u to the 1/2 is u to the minus 1/2. All of that times du. And now we can integrate. This is going to be equal to, let's see, add 1, multiplied by the reciprocal of that. That's going to be 2/3 u to the 3 over 2 by the power rule. And we're going to subtract. Add 1/2 to minus 1/2 is 1/2. Multiplied by the reciprocal of that is 2. So 2u to the 1/2, just like that. Do not forget to add that plus c. And last thing we need to do is don't forget to substitute back in your x's. We have 2/3. U is e to the x plus 1 to the 3 over 2 minus 2 times e to the x plus 1 to the 1/2 plus c. And you definitely could write that to the 1/2 as a square root radical if you wanted. All right, moving on. So for question 4, approximate the area under the graph of y equals x squared plus 1 and above the x-axis with x between 0 and 6 by using 3 rectangles of equal width with right endpoints. So right endpoints. Remember that you don't need to simplify your answer. So let's go ahead and sketch this real quick. We are between x equals 0 and 6. So we'll just draw this first quadrant because we're also above the x-axis. We'll say this is x equals 6. Obviously, this is 0. All right, y equals x squared plus 1. That's going to look something along these lines. The scale could be way off. And now, because we want 3 rectangles, we're going to say, what is 6 divided by 3? That's 2. And so that's going to be 1 at 2, 1 at 4. And now we have our 3 rectangles. And because we're looking at right endpoints, we're going to be going off this. This first rectangle is pretty small. You'll be able to see it more with this. We're definitely looking at right endpoints if we estimate the area like this. Perfect. All right, and now let's find the area of each of these rectangles. So let's call this R1, R2, R3. Well, each rectangle has a base of 2. That's pretty self-explanatory, right? Because we're using 3 rectangles over 0 to x. And then the height is actually going to be a lot simpler than it looks. All that's going to be is, well, what is the y value at x equals 6? Well, that's just f of 6. Same thing for this one, right? What's the y value at 4? It's going to be f of 4 and f of 2 down here. So we can write the area with this Riemann sum as the area. Let's say R1 plus R2 plus R3. This is going to be equal to, well, R1 is going to be the base times the height. So that's going to be 2 times f of 2 plus 2 times f of 4 plus 2 times f of 6. Not sure why I put a parenthesis in there. All right, so now let's just calculate each of these values. So we have, put a little asterisk here, f of 2 is going to be equal to 4, or actually, I'll write it out explicitly, 2 squared plus 1, which is 4, plus 1, which is 5. F of 4 is equal to 4 squared plus 1, which is 16, plus 1, which is 17. And f of 6 is equal to 6 squared plus 1, which is 36, plus 1, which is 37, just like that. So now we can write our area. We can say A is equal to 2 times f of 2 is 5 plus 2 times f of 4 is 17 plus 2 times f of 6 is 37. And again, this is where I would cut off my answer on a real exam. I'll keep going just in case you do it differently. 2 times 5 is 10. 2 times 17 is 34. Yeah, that sounds about right. And 2 times 37 is 60 plus 14, which would be 74. Yeah, 74. All right, and adding this up, let's see. This would be 108 plus 10, 118. Yes, arithmetic is not my strong suit. All right, moving on to question 5. We have consider the function f of x is equal to x to the 4th minus x to the 3rd plus 7. So we want to find for what values of x is the function decreasing. So decreasing or increasing, you're going to want to look at the first derivative. So let's do that. We can see f prime of x is going to be equal to 4x cubed minus 3x squared. And the way we're going to do this is to find when it's decreasing, we want to find when it's negative. And to find when it's negative, we can actually look at when it's 0 and then look at either side of that. So let's do that. We have f prime of x is equal to 0. This is equivalent to 4x cubed minus 3x squared is equal to 0. This gives us, by factoring, we have x squared times 4x minus 3. This is going to be equal to 0 when x is 0, or when x is 3/4. Just like that. If you want to write this all out on scratch paper, go for it as well. Okay, so now what we can do is we can look at a number line. So again, like I said a second ago, now that we have these points, we know this is when it's 0, and on either side, it's going to be positive or negative. So this is called number line analysis. We're going to look at when it's 0, when it's 3/4, and we're going to look at either side of this. So let's start off on the left side of 0. We can plug in, let's go ahead, plug in -1. Any number below 0 would work. So f of -1, or f prime of -1, sorry. This is going to be 4 times -1 minus 3 times 1. Right, because I'm plugging -1 into this x squared here. This is going to be -4 minus 3, which is -7. We don't care about the actual value, we just care that it's negative. So we know f prime is negative below 0. Now let's go ahead and look at when f prime is between 0 and 3/4. So let's check 1/2, that'll work. And this is going to be equal to 4 times 1/2 cubed is going to be 1/8 minus 1 times 1/2 squared is 1/4. This is going to be equal to 4 over 8, which we can simplify to 2 over 4, minus 3 over 4, which is equal to minus 1/4. So again, f prime is going to be negative between 0 and 3/4, but it's 0 at 0, right? And then lastly, we can plug in a number bigger than 3/4, and the nicest number for that's probably just going to be 1. So we can plug in, we have 4 times 1 minus 3 times 1. This is 4 minus 3, which is equal to a positive, I'll just write plus to emphasize it, 1. So now here, we can use this number line to see that, well, f is decreasing on the intervals. We have from minus infinity all the way up until 0, and then we have from 0 up until 3/4. And then these are going to be non-inclusive bounds, right? Because at 0 and at 3/4, the derivative is 0. And then, of course, we can't have a closed bound on infinity. Okay, moving on to part B. We want to find where all the local minima, if any, of f of x occur. And all we need to find is the x coordinate. So actually, we already did all this work. Because the derivative is negative going up until 3/4, and it's positive coming out, that means we're going to have something like this, going down the derivative, and then it comes back up. And then at that point, we're going to have a minimum. So that's just going to be at x equals 3/4, and that's all we need. All right, now for part Z, part Z, part C, for what values of x is the function concave up? So concavity means you're going to be looking at the second derivative. So let's go ahead and grab the first derivative from up top. We have f prime of x is equal to 4x cubed minus 3x squared, right? Yep. All right, so now let's find the second derivative. We have f double prime of x. This is just going to be equal to, by the power rule, we'll have 12x squared minus 6x. And we're going to do the exact same kind of number line thing. We have that f double prime of x is equal to 0. This is equivalent to 12x squared minus 6x is equal to 0. And now we can factor this. We have 6x times 2x minus 1 is equal to 0. This is going to be equal to 0 when x is 0 or when x is 1/2, just like this. And so now what we can do is we can do our number line again. So let's look at this. This time, instead of looking at f prime, we're looking at f double prime. And there are points at 0 and 1/2, the inflection points, right? So let's plug in some numbers. Let's go f double prime of minus 1, should probably work nicely. We can see 12 times minus 1 squared is just going to be 1. Minus 6 times minus 1, this is 12 plus 6 is 18, which is positive. Then we have f double prime of, we're going to need a number between 0 and 1/2, so we'll have to use 1/4. This is equal to 12 times 1/4 squared is going to be 1/16, minus 6 times 1/4. This is equal to 12 over 16 minus 6 over 4, which is 3 over 4 minus 6 over 4, which is negative 3/4. Again, we don't care about the value, we just care about the sign. That's negative. And lastly, let's plug in 1. So we'll go f double prime of 1 is equal to 12 times 1 minus 6 times 1. This is equal to 12 minus 6, which is positive 6, which is positive. So now we know that f is concave up on the intervals. We have minus infinity to 0, and then, not 0, sorry, 1/2 to positive infinity, just like that. Nice. All right, moving on. So for question 6, we have a road running north to south crosses a road going east to west at a point P, right here. Car A is driving north, so this is going to be car A. Car A is driving north along the first road, and car B is driving east along the second road. At a particular time, car A is 10 kilometers north, so we'll say this is the particular time. We have 10 kilometers and to the north of P and traveling at 80 kilometers an hour. 80 kilometers per hour, 10 kilometers. While car B is 15 kilometers east and traveling at 100 kilometers an hour. How fast is the distance between the two cars changing at that time? Make sure to include units in your final answer. Let's highlight that because I will forget. Okay, so the way we're going to measure distance is, well, let's draw a line, and you'll see here, this is now a right triangle. So we can use the Pythagorean theorem. Let's say, hopefully you remember that. Well, let's call this distance z. We can say that z squared is equal to, we'll call this down here x, and this out here y. So we'll say z squared is equal to x squared plus y squared. And let's solve for z, just to make it a bit easier. This is going to be z is equal to square root x squared plus y squared. And we can, of course, just consider the positive part for this. And let's rewrite this in a way that's going to be nicer for some calculus. We'll write this as x squared plus y squared raised to the 1/2 power. And now for this, we're going to use our implicit differentiation. So we're going to differentiate everything with respect to t, right? Because we're changing with respect to time. So the derivative with respect to t of z is equal to the derivative with respect to t of this big quantity over here. So we have x squared plus y squared to the 1/2. And now this is going to differentiate just like everything else. So derivative of z with respect to t, well, that's just going to be dz dt. And on this right side, we're going to need to use some chain rule. So what is the derivative of anything raised to the 1/2? Well, we can just use power rule. We bring that power down, we keep the inside the same, and we subtract 1 to make it minus 1/2. And then we have to multiply by the derivative of the inside with respect to t. So all that's going to be the derivative of x squared. That's going to be 2x times dx dt. And the derivative of y squared with respect to t, well, that's going to be 2y dy dt, just like that. And now what we can do is we can start substituting. Before that, let's go ahead and cancel out this 1/2 with these 2's over here. So we'll get dz dt. We may as well rewrite this radical as well. 1 over square root of x squared plus y squared times this 1/2 is going to cancel, and we're left with x dx dt plus y dy dt. All right, let's go ahead and substitute in our values. So remember, x is equal to 15. This is at the certain time, right? Which is why we can start plugging the values. So at a certain time, we get that the rate of change in distance is, I don't think we're given the exact time, yeah. So at time, we have 1 over the square root of x squared is 15 squared plus y squared is 10 squared times x is 15, dx dt is 100 plus y is 10, dy dt is 80, I do believe, yep. And so now we can start simplifying. We get 15 times 100 is going to be 1500, plus 80 times 10 is 800. All of this over square root of, we have 225 plus 100. This is going to be equal to 1500 plus 800 is going to be 2300. We can factor out a 25 from this. So we have square root of 25 times, this is going to be 9 plus 4, right? And this is equal to 2300 over the square root of 25, it's just 5. Square root of 9 plus 4 is 13. And what we can do is say 2300 divided by 5, that should be, let's see, 460 over square root 13. And let's just put the radicals on top in case your teacher likes that. We have 460 times the square root 13 over 13. And then don't forget the units. This is the rate of change of distance. So that's going to be kilometers per hour. And that's it. Moving on to question 7. All right. For question 7, we have f of x equals 1 over x minus 3. And for this part A, we're going to have to use the limit definition of the derivative to find f prime of 4. So I'll go ahead and just write the limit definition of the derivative in case you forgot. So f prime of x is equal to the limit as delta x. Sometimes you'll see this as h as well. As delta x approaches 0 of f of x plus delta x minus f of x all over delta x. So let's go ahead and use this. So writing, we have f of x is equal to 1 over x minus 3. Now we have that f prime of x is going to be equal to the limit as delta x approaches 0 of, and let's just go ahead and substitute it in right away. We have 1 over x plus delta x minus 3 minus 1 over x minus 3. And all of this is going to be over delta x. Let's go ahead and rewrite this slightly as the limit as delta x approaches 0 of, bring this 1 over delta x out front, times 1 over x plus delta x minus 3 minus 1 over x minus 3, just like this. Sorry, it's a little bit messy, but should be able to see. I'll erase it and redo it. X minus 3, just like that. So now we can say that f prime of x is equal to the limit as delta x approaches 0 of, let's go ahead, write this as 1 over delta x. In this interior, let's make these have a common denominator. So this first one, we need to multiply by x minus 3 to get x minus 3 over x plus delta x minus 3 times x minus 3. And then we're going to subtract from this. The second term, we're going to multiply by this, the bigger term with the delta x. We'll have x plus delta x minus 3 all over x plus delta x minus 3 times x minus 3. Just like that, perfect. And now this is going to simplify to the limit as delta x approaches 0 of 1 over delta x times, on this top bit, x and x are going to cancel. Minus 3 and minus 3 are going to cancel. We're just left with a negative delta x. On the bottom, we get a x plus delta x minus 3 times x minus 3, just like that. And now we can say this is equal to the limit as delta x approaches 0 of, these two delta x's are going to cancel. We're left with a minus 1 over x plus delta x minus 3 times x minus 3. Perfect, just like that. And now we'll substitute in delta x is equal to 0. We're left with minus 1 over x minus 3 times x minus 3, which is equal to minus 1 over x minus 3 squared, which is, of course, what we would expect using our power rule, which is the one nice thing about these problems is you can double check your answer. Okay, but so now we want to find f prime of 4, right? So f prime of 4, this is going to be equal to minus 1 over 4 minus 3, and then square all that. This is minus 1 over 1, which is just minus 1. And that's the answer to part A, I do believe. Yep. All right, for part B, we want to find the equation of the line tangent to f at x equals 4. And for this, let's just use the point slope formula line. So we have y minus y1 equals m, or the slope, times x minus x1, right? And so to find this, we know x1, that's just our 4, right? This is a certain point. Now all we need to find is y1, right? Because we have the slope from the previous problem. So let's plug in f of 4. This is going to be equal to 1 over 4 minus 3, which is 1 over 1, which is just 1. So we have y minus 1 is equal to a minus x minus 4. And this should be a perfectly good answer. Yeah, it doesn't specify, so this should be fine. I'll go ahead and put it in y equals mx plus b form just in case. But you should be fine with this on your test. We have y minus 1 is equal to minus x plus 4. And y is equal to minus x plus 5, just like this. This is also an answer. Both of them, of course, are the exact same line. So, moving on to question 8. We have part A, write down an integral or sum of integrals that represents the area of the region in the first quadrant, where x and y are both greater than or equal to 0, bounded by the following curves. So let's go ahead and sketch this out just a bit. So the first curve, y equals x, well, that's just going to be a nice line going straight up. Y equals 1 over x, that's going to look something just like this. And y equals 1/2, well, that's just going to go under just like this. All right. So the points we're interested are 1, 2, and 3 right here. So this first point, well, we know that this is the y equals 1/2 line. So where does y equals 1/2 intersect y equals x? Well, that's just definitely going to be at 1/2, right? And then the second one, we want to figure out where, I'll write down the names of these as well. Where does y equals 1/2 intersect 1 over x? And you can do this on scratch paper or just in your head. Where does 1/2 equal to 1 over x? Well, that's definitely just at x equals 2, right here. X equals 2. And then this is the last one we're interested in. Where is y equals x the same as 1 over x? And this is going to be at x squared equals 1, or because we're only interested in the positive part, x equals 1. So x is equal to 1, and of course y is also going to be equal to 1. This is something I would probably recommend you do on your scratch paper. And now here, we're interested in the area of this region. And so the way we're going to do it is we're going to split it up into two integrals. I'm not sure if my orange is going to go over this yet. Perfect. Okay. We're going to look at this region because this is under the y equals x curve right here. And we're going to look at this region under the 1 over x curve right here, split along this line right here. So the total area is going to be equal to the integral, first from 1/2 to 1, of the top is going to be x, the bottom is 1/2, like that, dx. And then we're going to add to that the integral from 1 to 2 of the top bit is going to be 1 over x, the bottom bit is 1/2, and dx, just like that. And we don't need to compute the integrals, so that's going to be our full answer, just like that. Moving on to part B. So for this part, we have to write down an integral or a sum of integrals that represents the volume of the solid obtained by revolving the region enclosed by these three curves about the line y equals -4. So let's go ahead and sketch this just a bit. So we're going to have this. We're going to have this right here. So this is our x-axis, this is our y-axis. And now we have our first curve, y equals x squared plus 2. So let's go ahead, draw that just like this. And the line y equals 2, so that's going to, of course, intersect right here at the corner, or not corner, I suppose, at the y-axis. And lastly, we have at x equals 3. So we'll say x equals 3 is right here. And so this is going to be our region that we're enclosing. And now we want to revolve this around the line y equals -4. So down here, this is our axis of rotation. So the way we want to do this is going to be the volume is equal to an integral. And of course, this integral is going to go from 0 to 3, right, across this x along here. And the way we're going to want to do this is we're going to want to make two circles. The first circle, the radius is going to be the outside edge. So how big is it from basically way up here to way down here? And the way we can do that is we can say, okay, we want to take the top edge of this x squared plus 2, right? We have x squared plus 2. And then we want to subtract this portion down here because it's negative. So we're going to go minus a -4, just like that. And of course we square it because that's the area of a circle, right? Pi r, this is our r squared, just like that. Right, and now what we can do is we can subtract this inner radius. So that's going to be the radius from this bottom part down to here. So the way we're going to calculate that radius is we're going to say, of course, multiplied by pi, so it's a circle. But to calculate that radius, well, the top edge is just going to be y equals 2. And we're going to subtract a -4, just like this. Square it, and dx, just like that. And this, it's not clear about simplifying, so this may be okay. We can simplify pretty easily though. First thing we can do is factor out a pi. So we'll have pi times the integral of 0 to 3. And then inside this first squared portion, we're going to have x squared plus 2 plus 4 squared minus, this second bit is going to be 2 plus 4 squared dx. This is going to be equal to pi times the square root, or not square root, sorry, the integral from 0 to 3 of x squared plus 6 squared minus 6 squared dx. This is equal to pi times the integral from 0 to 3 of, let's expand this out, we get x to the 4th plus 12x squared plus 6 squared minus 6 squared, just like that, dx. These two 6's are going to cancel. We're just left with the pi times the integral from 0 to 3 of x to the 4th plus 12x squared dx, just like that. And that's our final answer for the volume. Moving on to question 9. Okay, so for this question, we have the graph of y equals f of t below, and we define the function g of x, where it's the integral starting at 1, right here, of f of t dt for all real numbers x. All right, and now we're going to answer the questions below with no justification. So first off, we want to find g of 3. So g of 3 is just going to be the integral from 1 to 3 of this function. So we can find the area under this curve of this portion right here. Try to make it pretty clear right here. And this is just a triangle with a base of 2 and a height of, not sure if you can see it, it's going to be 6. Quality's not great here. Okay, but so this area is just going to be equal to 1/2 base times height. So 1/2 2 times 6. This is just going to be equal to 6. So the area, or sorry, g of 3, I suppose, is equal to 6. All right, now we want to look at whether g of 7 is positive, negative, or 0. So g of 7, all that that's going to be is it's going to be the area of this whole triangle, I'll shade it in here, minus the area down here, right? Because the areas under the curve get subtracted. And because we can see this area up top is much larger than this area down bottom, if you really wanted, you could count the squares literally. We know that this g of 7 is going to be positive. So we can shade that in. All right, next up, we have to find the x values for the local minima of g of x on the interval 0 to 12. So to find local minima, we want to look at the derivative of g of x. And the way we're going to do that is with the fundamental theorem of calculus. We can say that g prime of x is equal to the derivative with respect to x of the integral from 1 to x of f of t dt. And this is just going to be equal to f of x. That's it, actually. So to find when g prime, or I'm sorry, the local minima of g, we want to find when g prime is equal to 0. And since g prime is just equal to f, we can find when f is equal to 0. So that's going to happen once right here at 1, and it's also going to happen again right here at 5.5, okay? And so now what we want to look at is because g prime is equal to f, we know that, let's write like a little number line here, our number line analysis from earlier. So if we look at g prime, we know that it's going to be 0 at 1 and at 5.5. Before 1, g prime is negative. After 1, it's going to be positive, right, because it's in this upper section. And after 5.5, it's going to be negative again. And so to get a minima, we're going to look at this negative and then positive portion. So the only x values for which g of x is going to be at a local minima is going to be x is equal to 1, just like that. All right, so now, does g of x have any inflection points? If so, list their x values. If not, clearly state it does not. So because we know g prime of x is equal to f of x, we can just differentiate again. Get g double prime of x is equal to f prime of x. And so now we know that inflection points occur when the second derivative is 0 or undefined. So in this case, we're looking for when f prime is 0 or undefined. And so just by looking at this graph, well, we can see one point here up at the top. F prime is clearly undefined because this is a sharp turn, right? And this occurs, I've made a bit of a mess out of this, but at x is equal to 4, or t is equal to 4. So we have x is equal to 4. Yeah, sorry, not t. And now the only other point where f prime is going to be 0 or undefined, actually, no, sorry, there's a few more. We're going to have one point down here. This is right about at x equals 8. We have another point where the derivative is going to be 0. And the last one right here at x equals 10. Yeah, this one's not quite lined up. I'm not sure why that is. But yeah, now it's going to be at x equals 8. Okay, that is our final answer. So moving on to our final set of questions, I believe. Yep. Question 10, this is going to be some true-false questions. So for this first one, part A, for any function f of x, the integral from 1 to 5 of f of x dx is strictly greater than the integral from 4 to 5 of f of x dx. This question, first thing that comes to mind is let's plug in 0. So let's say we have the integral from 1 to 5 of 0 dx, and We don't know yet, but is it greater than the integral from 4 to 5 of 0 dx? Well, the integral of 0 is just 0. The integral of 0 over here is just 0. It doesn't really matter our bounds, so this clearly doesn't hold. This is a contradiction, so this is false. All right, moving on. The limit as x approaches infinity of e to the kx is equal to infinity for any value of k. This, we can actually do a similar thing. Well, let's say what happens if k is equal to 0? This is going to imply that the limit as x approaches infinity of e to the 0 x is equal to infinity. But this is just the same as the limit as x approaches infinity of 1 is equal to infinity. But this is just 1 is equal to infinity, which again is a contradiction. So this doesn't hold. This is false. Next up here, we have the integral of 1 over 1 plus x cubed dx is equal to natural log of 1 plus x cubed plus c. And you may notice right away this is false, but I'll go ahead write it out. Let's go ahead and take the derivative of this side and see if we get back to the integral function. So the derivative, just recall, the derivative with respect to u of natural log of u is u prime over u, and maybe that gives away why it's wrong as well. But if we take the derivative with respect to x of natural log 1 plus x cubed, this is going to be equal to u prime, the derivative of the inside is going to be 3x squared over then the inside 1 plus x cubed. This right here does not match with this right here, so this is going to be false, just like that. Moving on to part D, if the limit as x approaches 2 of f of x is 5, then f of 2 is equal to 5. Now, this will be true a lot of the times with our nice continuous functions, but let's say we have a function like this, where it's a line, we undefine it right there and put it up here, and then we keep going and say this happens at x equals 2. Well, the limit is going to be down here, but of course, our actual value is up here, so this is false. This is not always true. All right, lastly, the graph of y equals ln x has no horizontal tangent lines. So just recall, a horizontal tangent line is when the derivative is equal to 0. So if we have y equals ln x, we also have, I really hope that AirPod's still going, just to give me a sound, dy dx is equal to 1 over x. And now this is going to be equal to 0. 1 over x is equal to 0. Well, when does this happen? This only happens as the limit approaches infinity, which is not a horizontal tangent line we would consider. That'd be more of a asymptote type thing. But even then, we don't have any asymptotes. We don't have any horizontal tangent lines. So this is true. No horizontal tangent lines. And that is it. So if you made it this far, nice job.